This is the circuit of a MOSFET differential amplifier, and this is an application of the circuit analysis that we talked about last time. The amplifier that we studied last time does not look like this one, but we will see how we can use the results from last time to analyze a circuit that is implemented using just MOSFETs and P channel. So let's consider this circuit and see how it looks like or how it's different from the one that we had last time. Notice that we have the two MOSFETs here, M1 and M2, just like the differential pair. We call this a differential pair from last time. And this is exactly the same differential pair we had previously. And we have an output which is taken between the two drains. So that was also one of the options for producing an output, considering a voltage as the output between the two drains. The other options were use this signal to ground or this voltage to ground, or plus here and minus here. All of these are valid options for output. In this case, we're taking the output as you can see here, and this is called a differential output. So this is a differential amplifier with a differential output. Right, now the difference starts from here. This is a MOSFET, and it was supposed to be a current source. So we have a MOSFET instead of a current source. And here we had two resistors, and now we have two MOSFETs. So are these the same thing? Can we consider this to be a current source and these two to be resistors? Let's focus first on this M5. And let's say I want to actually implement the current source using a transistor. We know that we can do that by using the current mirror circuit. And this M5 would therefore be part of this current mirror circuit. The other part that I am not showing would be the reference here. Imagine the reference and another MOSFET with the gate shorted to drain and producing the bias voltage that comes here and biases M5 properly to produce the right ISS. So this means that, yes, I can use a MOSFET as a current source, provided that here I have the rest of the current mirror circuit, which we are not showing. We're just showing that I have a V bias that comes from that. All right, so this explains that why we have M5 and that it acts as a current source. What about M3 and M4? Can I consider them to be resistors? Here we have to consider how they affect, how M3 and M4 affect the rest of the circuit. So for M1, if we're looking into this drain of M3, what I will have is a MOSFET with gate at a DC level and source at DC level. So no signal here, no signal here, and I'm looking into its drain. And we know from our previous rules that when I look into the drain of a MOSFET with no signal at the gate and no signal at the source, I see the small RO of this MOSFET. And therefore, between this node here and this ground, there's a small RO3. And that's great because now I can consider this small RO3 to be my RD from last time. Same for M4. And I will have here a small RO4 from the drain of M2 to ground. So RO4 here, and it's also connected just like RO3. Now, if these two are matched, and they should be, the value of RO3 and the value of RO4 should be equal because they are matched and they are biased at the same current. And RO3 and RO4 are equal and they replace the RD of last time. This MOSFET is acting as really a resistor. This MOSFET is acting as a resistor, or its presence is felt as if it's a resistor. And this MOSFET, we said, no, its presence is felt as if it's a current source. Here, ISS, and it's mirroring something. Okay, so let's look at the questions here. The first question is, how do you generate V bias 1 and V bias 2? How do I generate V bias 1 and V bias 2? I already gave you a hint about how to generate V bias 2. This should come from the current mirror. So this is, I'm showing now the current mirror that is not there to keep the circuit schematic simple. But if I want to show it, this is how I would connect it. And here I will have the golden reference, IREF to, or maybe VDD. So IREF here. And this is how we can generate V bias 2 from a transistor. Let's say this is M6, and the reference, the golden reference, I can generate V bias 2, and this would bias M5 such that ISS over IREF is given by the current mirror formula W over L of M5 divided by W over L of M6, and assuming that there is no channel length modulation. If there is channel length modulation, then we have to correct to include the effect of lambda. Okay, let me take a pause and read the questions. Why don't M3 and M4 act like current sources or current mirrors? They're not. Their effect on the rest of the circuit is whatever we see looking into them. And when I look into the drain of this, I will see a small RO3. So this is in the small signal analysis. I don't know if this answers the question. I am using them. Let me answer the question about V bias 1, and then I will return to this question. لأنه because they are actually in the DC analysis, they're kind of generating constant currents, and but in the signal analysis they appear as resistors. Same for this, by the way. I mean, in the signal analysis, this will appear as the small signal resistance RO of M5. All right. So how do you generate V bias 1? The same way we generate V bias 2. But here I have P MOSFETs. So V bias 1 I can generate it using another reference current, which may be the same as this one. As a matter of fact, let me use the same one and generate V bias 1 from it. So erase this. And let's extend. Let's keep the eraser for now. And, eraser. And extend this to generate V bias 1 from it. Okay, so I will extend this to generate also V bias 1 using a P MOSFET. Using a P MOSFET. And this is how I can generate V bias 1. Okay, now this will get a bit messy. So this comes here. This is connected to this node. This is how I can generate V bias 1 and V bias 2 from the same golden reference and using the N MOSFET with drain connected to gate to generate this voltage needed at the gate of another N MOSFET, and P MOSFET with drain connected to gate to generate the voltage needed at the gates of the P MOSFETs. All right, so let me clarify. Maybe I did not clarify that in the small signal analysis, this current source, ISS, in the small signal analysis will appear as a resistor, as the small signal resistance, that is the output resistance of the current source, which is in RO5. We know that in this case. So that's the resistance looking into the drain of M5. And we have a DC here and a DC here. So the situation, the condition of M5 is similar to M3 and M4. And when we do the signal analysis, we will have here RO3, RO4, and we will have here RO5. And these two, if you want in the DC analysis, they're acting as if they're biasing the MOSFET. And this is similar to the common source amplifier that we studied a long time ago now, where we said that I can use a current source here instead of a resistor, and this will bias the MOSFET properly. And in the signal analysis, it provides a resistor, which is small RO of the MOSFET that is implementing this current source. So this is what's happening here. And it's also happening here. But I was trying to make this look like the circuit that we had last time. And the circuit that we had last time, let's very quickly go there, was something like this. So this is RO3, RO4, and ISS. This is the MOSFET M3, MOSFET M4, and the MOSFET M5. Now, in the signal analysis, I will see here RO3, RO4. What would I see here? M5 would be replaced by its small signal resistance, the small signal output resistance of the current source, which is small RO5. And the next question is, what is the voltage gain? What is the voltage gain in this case? Last time we said that we had several gains. We had something called the differential gain. The differential gain, this is the output divided by VD, or VID, which is the difference between the two inputs. And we had a common mode gain, which is the output divided by the input, or inputs when they're equal. We also had options of taking the output from different nodes. Now, the options here are for the output are clear, plus here and minus here. So there, I don't need to guess where's the output. But what about the type of voltage gain? And this question, what is the voltage gain in such a circuit, is not complete. It doesn't make much sense. I need to know, is the question about differential, or is it about common mode? So to be able to answer this, I need to insert here differential. What is the differential voltage gain? And then I can answer the question. Differential. Okay, this is so AD or ACM or common mode gain. I need to know that before I can answer. Let's say that this we want AD, and now if I want to find AD, and this circuit can be simplified to look like the circuit of last time, I can use the results from last time. Last time we said that when we have differential inputs and I want to find a quantity like AD, if this goes up by 5 millivolt, this will have to go down by the exact same amount. So it will go down by also 5 millivolt. When this goes down by 3 millivolt, this will go up by 3 millivolt. When I have such a case, we said that by what we call the seesaw effect, there's no signal here, and this is like a virtual ground. So this is a virtual ground when the two inputs are purely differential. Whenever this goes up by a certain amount, this goes down by the exact same amount. When this happens, this does not move. No signal appears here, and this is a virtual ground. And then this part of the circuit would be like a common source amplifier. And also this part of the circuit will be like a common source amplifier. And we can analyze this part of the circuit using the half circuit technique. And this is a very nice technique because it allows us to use all the previous results from common source in the case of differential. So if I have a virtual ground horn here at this node, this becomes like a common source amplifier with M1, the amplifying MOSFET, and RO3, the resistor between this drain and the supply, which is signal ground in the signal analysis. And we showed that the gain would be half GM RD or R prime L. This is the general result for the common source. R prime L in this case would be RO3 in parallel with RO1. And when I take the output differentially, then the gain will be half plus half. So I get GM times R prime L, not half of it. And GM R prime L will be GM1, which should be equal to GM2 because these are matched and biased at the same DC current. GM1 or GM2, so GM times RO3 parallel RO1, which should be equal to RO4 parallel RO3. A question by Paul, is there a virtual ground? So if there's a virtual ground, there's voltage between terminals of RO5. Okay, I misread. There is a virtual ground there. If there is a virtual ground there, the voltage between terminals of RO5. Yes, indeed. In this case, yes, there is no signal current that will flow in RO5 in this case. Yeah. And that's why RO5 does not affect the result. All right, so we can use the result from last time, and when I take the output plus here and minus here, I will get a gain which is AD is plus sign, because if I take the input here, I have a minus sign from gate to drain, but there is a minus sign already, so I don't need to include minus GM. R prime L, as we said, is RO1 parallel RO3. This is the gain of this differential amplifier. And remember, I need to say what kind of gain. This is the differential gain. Because if the inputs are equal, I will get something else. All right, now let's answer the question, what is ACM? ACM is calculated when the two inputs are equal, and I look at the output, and I need to know what is the output in this case. If the current source is ideal, but it's not in this case. If it's ideal, then the common mode gain will be 0. It's not ideal in this case, and we will have some signal at the drain here and a signal at the drain here. But remember that when the two inputs are equal and all these MOSFETs are matched, I have perfect symmetry. So instead of going to the formula and checking the previous slides and so on, I'll just use logic. This input is equal to this input. Everything else is matched. So this output will be equal to this output. Now, since my V out is the difference between this drain voltage and this drain voltage, when I take the output differentially, even if this is non-ideal, ACM will be 0. ACM is 0 because I am taking the output differentially. Even with a non-ideal current source, if the output is taken differentially, because of the symmetry, this drain voltage is equal to this drain voltage, and ACM will be 0. I don't need to check any common source or previous equations. So CMRR would be infinite. CMRR is 20 log base 10 of AD divided by ACM. Because ACM is 0, CMRR is infinite. Okay, let me pause here and see if you have any questions. Okay, was this easy on a scale from 1 to 5, where 5 is extremely hard and 1 is extremely. Whoa. Okay, I need other data points. Jason is saying -1, so it's beyond trivial. Makes sense. Great. All right. Okay. I can hear the microphone. If someone, please mute your phone, your microphone. Okay, let me try to mute your microphone here. Okay, that was Nizar. Right. Since you're in general feeling that this is easy, let's up it a notch. Let's look at a more challenging circuit. This one. This is, what is this? That's an awful lot of MOSFETs here. And this actually is a cascode implementation of a CMOS differential amplifier. Cascode implementation of a CMOS differential amplifier. All right, let's identify the different components, starting from here and the differential pair. And this is the differential pair, and that's clear. This is the input. This is the input. These are my two inputs, M1 and M2 are the differential pair. Their sources would be connected together and connected to a current source. This is supposed to be a current source. All right, is M9 and M10 implementing a current source? Yes, we can implement a current source using not just one MOSFET, but two. And this is something that we covered when we talked about the cascode amplifier and the benefits of cascoding. And one of the benefits was that if you cascode two MOSFETs like this, and you're looking into the drain of M5, you see a very large output resistance. And therefore, when we have something like this, we will have in DC, we will have a fixed current because I have DC voltages here. So I will have a fixed current, a DC current flowing. This is the bias current, ISS, that I need. But now in the signal analysis, the output resistance will be much bigger than the case when I only have one MOSFET. If I have one MOSFET, I am looking into its drain, I will see small RO of that MOSFET. If I have two MOSFETs cascoded like this, I will see something much bigger. I will see, and this is a formula in our formula sheets, RO9 plus RO10 plus GM9, RO9, RO10, which is much, much bigger than just RO9. This may be 20, 30 times, 40 times bigger. So that's good. Why is it good? Because if I want to build a current source, a good current source, I want to make it as close to ideal as possible, and I want to make its output resistance as close to the ideal output resistance as possible, which is infinite. The ideal current source has an infinite output resistance. The current doesn't change with voltage. The DC current does not change with voltage. So making the output resistance larger by cascoding two transistors will give us this nice large output resistance. So this is why we have a cascode here. Okay, let's go back to our differential pair. And in the previous circuit, the outputs were taken from the drain of M1 and the drain of M2. Now, where is the output? And the output is here. The output is taken from the drain of this M3 and the drain of M4. And we can identify too that this is a cascode. This is like a cascode stage where the input comes at the gate of the first MOSFET and then goes to the source of the second. And this is a common source and this is a common gate, and we take the output from the drain of the second MOSFET. So again, this reminds us of the cascode amplifier. So this also is a cascode amplifier. And the same is, we see it here, the exact same thing. And then the output is taken here. So this is the cascode amplifier with the common source, common gate. Same thing here, exactly, common source, common gate for the second input. And the output is taken between the two drains. Okay, I think we can go now to this part here. And what is this? Now, this is implementing in the differential amplifier circuit that we saw. This is implementing RD and RD. And here, what would be the RD from this output, from this node to ground? It will be the resistance seen looking up. And here again, I see the same situation. I have the same situation as here. And my RD is very large. My RD is very large because it's RO5 plus RO7 plus GM5, RO5, RO7. So I see a very large RD. So this is the replacement of RD, which is a large resistor. Same here. So this cascading of these two MOSFETs would give me a very large RD, very large RD. And I have a cascade amplifier with a large RD to supply. I have a cascade with a large RD to the supply, and the cascade is built in a differential way with two inputs coming at the gates of the two MOSFETs M1 and M2, and the current source is implemented using two MOSFETs, and also it has a very large output resistance. And now, how do I analyze this? Let's see the question. What is the voltage gain? What is the voltage gain? Okay, we're confused again because in these circuits, what did we just say? And this, you cannot ask this question. And this is not a valid question. You need to tell me, are you asking about differential gain, or what's the second one? Common mode gain. And you need to tell me where's the output. All right, so here we have an indication that the output is taken between the two drains, but that's not enough. Is it plus here, minus here, or plus here, minus here? I will get plus or minus, so that's fine. Let's take plus minus. If I need plus minus like this, then I just add a minus sign to the results. Okay, so this is the output, but still I can't answer this question. I need to know, do you want AD or ACM? Which one? Let's start with the easy one. Which one is the easy one? ACM is trivial again, because if the two inputs are equal, I have perfect symmetry in the circuit. The drains will be at the same signal or DC or whatever voltage. Everything we see here will see exactly the same here. So if I have a voltage here, I will get the same voltage here. And therefore, what's the difference between them? 0, and ACM is 0. And this is trivial. If the voltage was taken from one side, if this was my output, just the drain voltage here, the signal at the drain of M3 to ground, if this is my output, then I would have an ACM, and I will need to get the equation from some previous slide or from the common source, common gate equations, or the cascade equations. What about AD? AD is when I have uh, differential inputs. So when this is VID over 2 and when this is minus VID over 2. And I have to find V out over VID, the difference between them. All right, if I have VID over 2, if this goes up by this much, this will go down by the exact same amount. And again, we're back to our virtual ground here when the two inputs are differential. If this goes up this much, this goes down by the same amount, and this is a virtual ground. Let's see. So this will be a virtual ground when I have differential. And therefore, I don't need to worry about this part. I can ignore completely this part now. And for this part, I will have an RD, which is RO5 plus RO7 plus GM5 RO5 RO7. And now the half circuit, which is this, with an output here and an input here, which is equal to VID over 2, is exactly like a cascode amplifier with a resistor equal to RD. And this means that I can go back to the cascode gain formula and use it as is. And so I say this voltage VO1 or VD3 over VID over 2 is the cascode gain formula. And then this voltage, same thing here. This voltage, VO2 or VD4 over minus VID over 2 is equal to the same formula. And V out over VID, I can replace and find very easily. So even this circuit, which at first appears to be complicated, very hard to analyze, we can analyze it by simplifying it to things that we already know. So there's nothing really hard here. Let's move on to the BJT differential amplifier. And last time we showed that this BJT differential amplifier does in fact reject common mode inputs when the two inputs are equal. And now let's show that it amplifies differential or differences between the two inputs. So again, we do a small signal analysis, and this is what we get. Before I show this, before we show the small signal equivalent model, that's not what we get when we do small signal analysis. Actually, this is a circuit with a modification of this one, and the modification is adding this RE here. So this is the original one without the RE, and this is the modified one with the RE. The reason we add this RE is two things actually. One is to increase the input resistance, and the other is to increase the linearity in the circuit. The bipolar transistors are exponential devices, and therefore any small signal, anything that's more than a few millivolts, will get distorted. By adding this resistor, then we can have larger inputs that do not result in a distorted output. And this becomes a special case of this. If RE is 0, then I go back to this. So this is the more general differential amplifier in the case of the BJT. All right, so this is now the small signal analysis using the T model. And if I don't have the big RE, this is the T model. This is the first BJT, small RE, GM1 V pi 1. This is second. small re gm2 v pi 2. And because these two transistors are matched and they are biased at the same current, they will have the same gm and the same re. In this case, I will have an input current. Unlike the MOSFET case, I will have an input current and an input resistance. And we can relate this current to the base current using IE equals beta plus 1 IB. So IE1, this current here, is V pi 1 over RE, and V pi 1 is 1/2 the VID when the two inputs are differential. So this gives me the value of IB1. And the input resistance is therefore the input current, input voltage, in this case, the differential voltage VID divided by the input current, which is IB1, which is also equal to IB2. And I get 2 into beta plus 1 RE or 2 R pi. So the input resistance in the case of the differential amplifier is 2 R pi, and R pi of Q1 plus R pi of Q2. 1 R pi comes from Q1 and 1 R pi comes from Q2. If I have the big RE, then instead of just small RE, I will have small RE plus big RE, and that's how the big RE increases the input resistance. It appears beta plus 1 times bigger. What's the differential voltage gain? We can show, similar to the MOSFET case, that on the first collector, I will get minus GM over 2 times RC times VID, and on the second collector, I will get GM over 2 times VID times RC. And if I take the output from between the two collectors, I will get the same formula as the MOSFET case. Instead of minus GMRD, it's minus GMRC. And if I take the output as VC2 minus VC1, I will get plus GMRC. If I have RE, I will add, I will modify the formula to take RE into consideration. So again, if I don't have an ideal current source, the node between the two emitters, connected to the two emitters and the current source, when the two inputs are differential, will be at signal ground. I will have a virtual ground, and these results apply even if I don't have an ideal current source biasing the two transistors. So I'm calculating now the common mode gain, and I will use the half circuit technique. So here I will need to consider the output resistance of the current source and then split it into two parts. So back to this circuit. Here, this is my IEE, and now I'm saying that it's not ideal, so it will have an output resistance in the signal analysis equal to REE. But then I want to split this REE between the two parts of the circuit. So I will have 2 REE here and 2 REE here. It's really just the output resistance of the current source, but I want to make it appear as if it's two things. One resistor equal 2 REE here, and in parallel with it, another resistor equal to 2 REE here. And now when the two inputs are equal, this part of the circuit and this part of the circuit will be exactly symmetrical. And both of them will be, as we will see, will be exactly like this, and will be a common emitter amplifier with an emitter resistor equal to 2 REE. And which means that I will have an output when there's a common mode input. If the current source, which was here, is not ideal, I will have an output. If it's ideal, I will not have an output. But even if it's not ideal, with an output resistance, and I see a voltage here, and I see a voltage here, they're equal, and therefore, if I take the output differentially, they will cancel out, and the output will be 0. I will not see a difference between the two. And in this case, such an output will be 0. even though here I have a signal and here I have a signal. And if ACM is 0, the CMRR will be infinite. If I take the output single-endedly, that is from one collector to ground, then this is the approximate ACM that I will get, and this is the CMRR. Why is this an approximate ACM? Because this is the exact formula here. This is the formula coming from the formula sheet for a common emitter amplifier with emitter resistor. This is a common emitter amplifier with emitter resistor. So if I look up the formula, I will get this. So how is this equivalent to this? It's not equivalent, but it's a very good approximation. Alpha is very close to 1. So there's like a 1% error here. And this RE and this 2REE, this is usually in ohms and maybe tens of ohms, and this is usually in hundreds of kilo ohms and mega ohms. So if this is like 1,000 kilo ohms and this is 50 ohms, I can easily remove it. And therefore, this is a very good approximation. And here's an implementation using P&P BJT instead of the resistors. How can we implement the current source? هات نشوف your guesses. How can we implement a current source like this in a BJT circuit? What's the simplest way to implement such a current source? Yeah, this can be just another BJT. Here's how I can implement it using a BJT. With a bias voltage here that's coming from a reference current and a BJT with collector shorted. So something like this. This is a very simple IEE. And what about the RC? What happened to the RC and RC that were here? Q3 and Q4, the small RO3 of Q3 and the small RO4 of Q4 are acting like the RC in this case. So in the previous formulas that we derived, what would be RC here? RC is small RO3 or RO4 equal to RO4 because they're supposed to be matched and biased at the same value of DC current. And what is REE? The output resistance of the current source. If I implement this using just one BJT like this, simply RO, let's call this Q5, simply RO5. So, and then I can use all the formulas from the previous slides. But notice that here I'm taking the output between the two collectors. So that makes ACM 0. Common mode gain will be 0. Okay, we have a few more minutes. And before we stop and discuss the assessment, the midterm, and the short quizzes, again, the voltage gain, this is getting annoying, the same question that doesn't make sense. All right, so let's see. Right, okay. I need to know AD or ACM. And if it's ACM, we said because I'm taking the output between two collectors, it will be 0, even if this current source is implementing using a BJT. What about AD? AD in differential, I will have a virtual ground here. And with a virtual ground, I will have a simple common emitter amplifier, and I can use the previous result from the previous slide. And again, the answer is easy.